All right, welcome you guys. So we are going to start chapter 8. We are going to cover 8.1 through 8.3, which is sequences and series in general. And we're going to cover two specific sequences and series, the arithmetic and the geometric. Okay, so let's start off with general, like what is a sequence and what is a series in this section 8.1. So basically a series is just a list of numbers with commas between them. Now it could be a list that stops. In that case, it'd be a finite sequence. Or we could have the ... at the end of it, which means that it's going to be an infinite sequence. And the terms, if we were going to describe them abstractly, would be a sub 1, a sub 2, a sub 3. So the third term would be called a sub 3. That's our notation for the third term. Or the nth term would be a sub n. Okay. All right. So let's go ahead and take a look at, for graphing these, what the difference is between a function and a sequence. Okay. So if you come down here, you can see we have the f of x notation. We have x's here. And over here, we have a sub n notation, and we have n's here. But basically, you're going to substitute in a number and get a value for both. But what's different is the values we're allowed to substitute in. For a function like this one, the domain is going to be all real numbers. So I could substitute anything in that I want. I could substitute in square root of 2 if I wanted to. I could substitute in a half, and I'll get a value out, right? Okay. So the domain here is all real numbers. But if you go over here to a sequence, the domain is not all real numbers. The domain is the natural numbers. So the very first number I'm allowed to substitute in is 1. Then the next number I'm allowed to substitute in is 2, etc. Okay. So for example, at a half, well, that wouldn't make any sense because what you're saying here is the first term is 3. The second term is 5. There's no such thing as a half term, right? You have a first term, a second term, a third term in the sequence. There's not going to be a half term in the sequence. So you should have disconnected data here, or discrete data, versus here you have continuous data, okay? And they'll match, at the integer or the natural number values, right? So they will have the same exact value at 1. They'll have the same exact value in x is 2, or the same exact value in x is 3. But resist the urge to connect these because that wouldn't make any sense if you were graphing a sequence. All right. So let's go ahead and start off with what I think is a pretty simple section, hopefully. I hope you guys find it. There's no graphing. So I know a lot of students don't like graphing. It's more of computational. Okay. All right. So it says find the first 4 terms and the 20th term. So we have to find the first term, which means we're going to substitute in a 1. We have to find the second term. So we're going to substitute in a 2. The third. The fourth. And the 20th. We're just plugging in 20 to show you that when you have a formula like this, an explicit formula, it's so easy to get any term somewhere down the line. Okay. All right. So 1 squared is 1, and 1 plus 5 is 6. So basically, you would say a sub 1, 6. You got to get a sub 2, third term, fourth term, ... Okay, so for the next one, 2 squared is 4, and 4 plus 5 is 9. Then 3 squared is 9, and 9 plus 5 is 14. And 4 squared is 16, and 16 plus 5 is 21. And then finally, 20 squared is 400, and 400 plus 5, that's 405. Okay, so that's going to be our answer for the first 4 terms in the 20th term. Same directions. So on this one, really dealing with the negative and the math's a little bit tougher than the last one. But I mean, if you have if you're allowed a calculator in your class, then these aren't tough at all. You just substitute these into the calculator. I will probably do it by hand just because, I don't know who I'm working with here. So I want to make sure we could do it by hand if need be. Okay, so we're going to start by substituting in 1, 2, 3, 4, and 5. All right. So let's see here. So we're going to end up getting 3 times -1/3. And you can just think of it as the 3's canceling. So really what's going to be left is -1. So our first term, a sub 1, is -1. All right. So now we just have to do, remember, you have to do the exponents first. So we're going to have to take care of the -1/3 times the -1/3 first, you guys. Okay, so a -1 times a -1 is a 1, and 3 times 3 is 9. So that gets us 3/9, and if we divide by 3, put both the top and the bottom, and we get 1/3. All right, let's try the next one. Well, a -1 times a -1 times a -1 will stay negative. 3 times 3 times 3 is 27. So this time we're going to have 4 of them, right? Whenever I have an even amount, I like to pair them up. Makes the math a little easier. Like I'll combine these two and I'll combine these two. So it's really 3 times. Well, -1 times -1 is 1, and 3 times 3 is 9. So we're going to get a 9th and a 9th from each pair. So this is going to get us 1 times 1 is 1, 9 times 9 is 81. So if we multiply straight across, it's going to give us 3/81. Okay. Probably should have made it clear, you guys. There's a 1 in the denominator, right? Underneath these, you know what? I just realized I did not do the last one correctly. I forgot about the times 3. So if we multiply by 3/1, let me go fix that. Ooh, got it. Then we get -3/27. So if we divide by 3's to both, we're going to get -1/9. So let me go in and fix that. Spotted that. All right. Okay, so then same thing here. When we have 3/81, we can divide by 3 to the top and the bottom. And that's going to get us 1/27. Now, I'm just going to go ahead and use the calculator for this one because I'm not multiplying that 20 times, guys. All right. So we got 3 parentheses, -1 divided by 3 to the 20th. Holy moly. Oh, and it won't actually turn that into a fraction for you. That is interesting. Okay. All right. So I'm just going to round it in the 3rd decimal digit. So actually I won't. I think I might just leave this, you guys. This is just scientific notation. So basically it's going to be, what was it? 8.6, we'll say. 8.6 times 10 to the -10. And so if you're curious, like what that means, I mean, this is good enough, but it means that you would take your 8.6 and you would move the decimal place 10 times to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically it's going to put 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros in front of it. So it's that small of a number, which makes sense because the denominator is going to just keep growing and growing and growing. Look at our sequence so far, while the top stays a 1. So we are going to head towards 0. So that makes a lot of sense. Okay. So I'm just going to leave it in scientific notation. You can see why nobody wants to write that ugly decimal that I just put So we'll leave it like that. Okay. Now this particular sequence has a name. It's called an alternating sequence. The terms are going negative, positive, and they will continue to do that. Every odd term will be negative and every even term will be positive. Now, a lot of times you can tell an alternating sequence because it will have a -1 to some power like n or n+1 in it. So let's just kind of investigate these to make sure that you understand them deeply. So in the first sequence, I'm just going to substitute in a few terms so you can see what's happening. So I'm going to substitute in a 1, a 2, 3, and a 4. Well, when we take a negative and we raise it to an odd, it stays negative. But a negative times a negative will become a positive. Raised to an odd, it stays negative. Raised to an even, it becomes positive. Because you think about like pairing things up, like I did on a first example. Any 2 will become a positive. And +1 times +1 is still 1. So whenever you have an even, the pairs can pair up with each other and become positives. All right, and so what they're saying here, if you look at these directions, says for odd numbered terms, it should be negative. Well, that's true. Look at our odds, it was negative. Our odd, it was negative. Then for any even numbered terms, it's positive. Yeah, for the 2, it was positive, and for the 4, it was positive. This is important information because later on I'm going to ask you to write the sequence, write a formula for the sequence given the sequence. So backwards is what we're doing now. And if it's alternating, you'll want to know whether you should be using -1 to the n or -1 to the n+1. So if we look at the other sequence, sequence B, so if we substitute in a 1 into that one, a 2 into it, oops, 3 of them. Then this is going to be -1 to the second, which we know is going to be a +1. This one's going to be -1 to the third, which makes it stay negative. This one is -1 to the fourth, which makes it become positive. And this one is -1 to the fifth, so it stays negative. So what this does is it changes. Now the odds become positive. The odds become positive. And the evens become negative. The evens become negative. Okay. Sorry, I forgot to do the odd one for this one. Okay, so depending on whether or not you want the even ones to be positive or negative, or the odd ones to be positive or negative, you'll use an n or an n+1 as your exponents. And we'll revisit that later. Okay, so here's, given the sequence, basically write the formula that'll generate it. So one tip that I have, and I have these written down later, is that sometimes if the sequence has some roots in it or has some fractions in it, you might want to turn everything into a root or turn everything into a fraction. So once I do that, I think that we can see what the formula is that's going to generate this. So for example, 1 could be written as square root of 1. And 2 could be written as square root of 4. And so now it's kind of easy to see that you could write this as the square root of n. And you can always check whatever you write to see if it works. I always tell my students, don't put something on this test that you haven't checked. You can for sure see if you're right? When I substitute in a 1, do I get the first term? Yes, I do. When I substitute in a 2, do I get the second term? Yes, I do. Okay. So you could go in and see, is it giving you what you want? And it looks like it indeed is. All right, so what's happening here is we are adding 2 each time. So whenever you are adding 2, that actually becomes multiplication in the formula. Adding 2 in the sequence becomes multiplication by 2 in the formula. You might have to do some fudging, which is an example, a couple examples later, we're going to have to fudge. But on this one, we don't have to fudge, it's spot on. So this would be the sequence that would, or this would be the formula that would generate. Okay, so addition becomes multiplication. Let's check and see if this is right, you guys. All right, so if we check, we substitute in a 1, we get 2 times 1, which is 2. That got me the first term. If we substitute in a 2, 2 times 2 will give me 4, which is the next term. This looks like it's working. Now, what I mean by fudging is, let's say that the sequence had been adding 2, but it looked like that, okay? So we're still doing plus 2, right? From one term to the next. But 2n wouldn't cut it, right? That's not going to work this time. That's going to generate this sequence over here. So when you plug in a 1, you know that you're supposed to get 3, right? But we only get 2. So add 1 to it, and it should work now, okay? Because that will get you 3. For a sub 2, let's try it. If you plug in a 2, we get 4 plus 1, which is 5, and that generated the second. So I call this the fudge number, okay? You'll always be multiplying by 2, but what that fudge number is going to be is going to change, okay? All right. So this time I'm not adding 2. I'm actually multiplying by 2 to get from one term to the next. So if you're multiplying by 2, then that becomes an exponent on 2. So multiplying by 2 in the sequence becomes exponents with 2 as the base in the formula. And again, you might need a fudge number, but let's check this one out. I think this one's really straightforward. So I'm saying that 2 as the base and n as the exponent. Maybe I need to do more than n, like n plus 1 or n minus 1 or whatever, but let's try it, okay? So let's see if this works. For the first term, I get 2. For the second term, I get 4. For the third term, I get 8. This is checking out, guys. This is looking good. So I don't need to add any stuff like after the n, like maybe an n plus 1 or an n minus 1 or whatever. Okay. All right. So I like to think of this in 2 parts. I like to think of it as first, the -1 to the whatever, because I can tell it's an alternating sequence. And then I like to think of the numbers without the signs, okay? So my first question is going to be, should it be -1 to the n, or should it be -1 to the n plus 1 power? Yeah, that's what we want to tackle. Well, let's try this one, the first one, and see if it works. When I plug in a 1, I would get a negative. And the first one is negative. So this one is working. So I'm going to put here, first number is negative. So this is going to be the winner here. We're going to use that. Now, if I look at the sequence without the signs, okay? Take a look at that. And I just think about that. So 1, 3, 9, 1, 3, 9, 27, 81. Well, you can see that we're multiplying, right? We are multiplying by 3. Yeah, every time, right? So we know it's going to be 3 to some power, but this one's not going to work because when I go and I check it and I substitute in for the first term, if I substitute in a 1, I get 3. But I don't want to get 3. I want to get 1 for the first term. So this is when we have to do the fudging, okay? So if I subtract 1 from it, because 3 is actually the second term, so subtracting 1 from it should work. Let's see if it does. 3 to the 1 minus 1 gets us 3 to the 0, which indeed is 1. Okay, so this is the correct formula to generate the terms without the signs. So if we put the two together, here is our formula for this sequence. We need the -1 to the n to make the signs alternate. And then we need the 3 to the n-1 to generate the numbers that we want. Anything that you write down, you want to check, okay? So I'm going to go ahead and check it right now. So let's substitute in 1. And then we'll substitute in 2 and 3. Okay, so -1 to the first is -1. 3 to the 0, that will be 3 to the 0, right? So that'll be 1. And that gets us the first term. It checked out. Let's try this next one. -1 squared is +1. And 2 minus 1 is 1. So 3 to the first is 3. Well, 1 times 3 is 3. So that checks out. Okay, that's the second one. I might just do one more just to really make sure. This is a 3. And this is a 3 minus 1. -1 to the third stays negative. 3 to the second power would become 9. Oh boy, that's another 9. Let's try that again. So that's going to get us -9, and that's the third term. This is working. So I wrote down some of the things I verbally said to you guys, okay? That if you're adding the same number from one term to next, it will become multiplication by that number and n. If you're multiplying by the same number from one term to the next, it will become an exponent with that number as the base and n is the exponent. If the sign alternates, there'll be a -1 to the n or -1 to the n plus 1. If some numbers have radicals, try making them all radicals. Now there's more tips I could give you, but I was just looking at the sample set for my math for the Beecher book, right? That we're looking out of, the college algebra, Beecher, Pena, Bittinger. And it looked like that would be enough tips to get through what I at least saw in the textbook, okay, which usually my math lab correlates with. Okay, so now we're going to move on to a series. Now the difference between a sequence and a series is instead of commas, there's plus signs, okay? So we are adding up the sequence basically. So you could have an infinite series. It'll have a plus ... But you can also have a finite series. We just often don't call it a finite series. We call it a partial sum, which makes sense, right? It's like, okay, it stops because I only took part of it. So partial sum. So whenever I write S, that means that I'm asking you to add up an infinite series. This is going to mean the sum of an infinite series. S for sum. If I put S sub n, that subscript tells me how many of the terms I'm going to be adding. So this would mean add the first n terms. Or in other words, the nth partial sum. Okay, so let's take a look at this. For the sequence above, find each of the following. Find S sub 1, S sub 4. Well, this is kind of silly. The sum of the first 1 numbers, that would just be -2 itself, right? Now the sum of the first 4 terms, so that'd be -2 plus 4 plus -6 plus 8. That'd be the first 4. So S sub 4, those are going to make 2. Those are going to make 2. So it looks like S sub 4 is 4. When you get into calculus 2, at least at the sequence at our school, you actually revisit sequences in series, and we look at what a partial sum approaches as it goes to infinity to find an infinite sum. So this will reappear again in your Calc 2 series. Okay, or your Calc 2 class. Okay, so this would just be -2 plus 4 plus -6 plus 8 plus -10. So all it's done really is it's taken S sub 4 and added one more term, right? These we already know add up to 4 from the work we just did. We just got to tack on the -10 now, right? So it looks like the answer is going to be -6. All right, sigma notation. So you've probably seen this before. A lot of times it's used for sororities and fraternities. Or it's on Excel. If you open up your Excel, it'll be up in the top as one of the buttons you can click on. This is the Greek letter capital sigma, and it's used to denote a sum. The lowercase letter sigma looks like this, and that's used in math to denote the standard deviation in statistics. They're basically our S. So that's why we use it, S for sum, S for standard deviation. That's why we use it. There's one capital P, capital pi, which is like our P, and we use that when it's a product instead of a sum. Okay. So anyhow, we're going to have a sigma notation as a way of writing these series out instead of like listing them all, because that gets cumbersome. So like you could have a quick way of listing a series by putting down some lower subscript or lower index and an upper index, and then putting some sort of formula here. Okay, and then that's your way of saying plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, stop. And the sigma tells you to add them all. As I was saying a second ago, capital pi, you could do the same thing. You could have a lower index, sorry, have an upper index. But because it's a pi there, that would tell everybody, okay, multiply them all. Okay. So we have the notation. You won't use that, I don't think, maybe at your community college or whatever, but this one gets used quite a bit. Okay. So let's see if we can use sigma notation. All right, so the first thing we want to do is we want to substitute in 1, 2, and 3, and then when we get done, we'll add them. Okay, so we're going to substitute in 1 plus, we're going to substitute in 2 plus, and finally, we're going to substitute in 3. Stop. Okay, so 3 times 1 is 3, and 3 take away 8 is -5. 3 times 2 is 6, and 6 take away 8 is -2. 3 times 3 is 9, and 9 take away 8 is 1. Okay, so this looks like this is going to add up to -6. We evaluated the sum. Okay, let's do it again, but maybe for a more complicated. All right, so this time we're going to substitute in 1, 2, 3, and 4. Plus. So this is going to give us 2 over 1, 4 over 4, 6 over 9, and 8 over 16. So 4 divided by 4 is 1. And if we were to reduce by 3, and then by 8, we would have, what, 2/3 and 1/2. Yeah, which is really just 3 plus 2/3 plus 1/2. Okay, so we can just go and compute that really quickly. So 3 plus 2/3 plus 1/2. 25/6, you guys. Okay. Evaluate that. It's getting more complex as we move along, huh? Now this one doesn't start at 1. It starts at 3. So the very first number doesn't have to be 1 that we're going to substitute in. It doesn't have to be I that we always use for the subscript. In this case, it's J. And then don't forget plus in between each one. I'm going to substitute in 4. And then I'm going to substitute in 5 instead. Okay, so -1 to the 4th power. And then 3 times 3 just gets us 9. Well, -1 to the 4th will become +1. Anytime it's even, it'll become positive. All right, then for this one, it's going to be -1 to the 5th power times 3 times 4, which is 12. Well, -1 to the 5th is going to stay negative. And when I multiply that by 12, I'll get a -12. And then on the last one, -1 to the 6th times 15. So negative 1 to the 6th will become positive 1. And 1 times 15 is 15. 24 take away 12. This should be 12 for the final sum. I had to put this one in here because I remember the first time I saw it being kind of weirded out. So I just want to make sure that you've seen it. So there's nowhere for me to substitute in the 1, the 2, the 3, and the 4. So in this case, the first term is 10. The second term is 10. The third term is 10. And the fourth term is 10. And I'm going to stop there because it's only 1 through 4. So this would end up being 40. All right. So the way that we write these is not unique. And right here, what I have for you is a sum that is the exact same sum, but written 3 completely different ways, okay? So like just to check out this first one, right? We would substitute in a 1, a 2, a 3, a 4, and I'm just gonna stop there. On this next one, we would substitute in a 0, a 1, a 2, and a 3. But when you do the math to that, you still get 1 squared, 2 squared, 3 squared, 4 squared. So it still matches the first sum. Over here, we'd start by substituting in 2, then 3, then 4, and we finally stop at 5. So you get 1 squared plus 2 squared plus 3 squared plus 4 squared, you get the same exact sum. So if I ever ask you to write sigma notation for a particular, series that you have, you might not have the same thing as your neighbor, but you're both still right, okay? Now, of course, it might be nice for you to find the neatest way to write it. I think we can all agree this first one is the best, most efficient way to write it. So be looking for that. We always want to try to be efficient, but the other ones are technically correct too. Okay, so here we go. Putting everything together. Write the sigma notation for each sum. So the very first thing I would do is I'd get my sigma notation and I'd say, let I be 1, and then we go. So 1, 2, 3, 4, 5, 6. So it's going to stop at 6. Okay. All right. Now we can see, maybe it's easier to see here, that we are adding 2 every time. I always like to go to the positive numbers, you guys, so I can spot what's happening a little bit better. So we said that adding 2 becomes multiplying by 2. So that needs to be an I. But we're going to have a fudge number, okay? Because notice that when I substitute in a 1 into this, 2 times 1 gets me 2. And I don't want a 2 for my first number. I want a -3. So I have to think, what could I subtract from 2 to get a -3? And maybe you can see that it's a -5, but that'll do it. So I'm going to need a -5 attached to this to make this fit the scenario. Now let's go in and check. I told you anything you write down, check it, right? So if we check it before we box it, let's see. If I substitute in a 1, substitute in a 2, I probably won't check the whole thing. 3 would probably be good. And if I substitute in a 3, is this getting me what I want? Let's see. This one will become 2 minus 5, which is -3. This one will become 4 minus 5, which is -1. This one will become 6 minus 5, which is 1. It looks like it's working, you guys. You can see we already have the first 3 terms. So I'll just put plus up with that. I'm ready to box it. So we knew it was 2 times something because we were adding 2, but we had to figure out what we needed to subtract to get it down to 3. All right, so let's go ahead and write sigma I equals 1, 1, 2, 3, 4, 5 this time. So we'll have 5 be the top index. All right, So you can tell that it's alternating in signs. So I know there's got to be some -1 to either an n or an n+1, right? So we have to check and see, is it this or is it this? Well, when I substitute in a 1, I end up with a negative, but the first term's not negative. If I look at this one over here, when I substitute in a 1, I get -1 to the second, which becomes a positive. So this one is going to be the winner because the first term is positive, right? Oops. First term is positive. Okay. All right, so we're going to have to tack a +1 onto that. Now, if we think about the sequence of numbers without the signs, well, what's happening each time is we're multiplying by 2. So we said that becomes, multiplication becomes an exponent. So 2 to the n, and I might need to fudge that also, okay? When I substitute in a 1, that gets me a number that's too big. So maybe I might try downing it by 1. So let's try downing it by 1, you guys. So in other words, like a -1. Let's see what happens. 1 minus 1 would be 2 to the 0. It's still not small enough. So let's try downing it by a 2. One minus 2 is -1. Yes, that becomes a half. Okay. So we had to down it by 2. Another way to kind of see it is to write these numbers with 2 as the base. Oops, write them correctly. These are how you would write, like 2 cubed is 8, 2 squared is 4, 2 to the first is 2, right? So what you can see is I'm going to have to, where the 1 is, always go to where 1 is. We had to back it up 2 spaces, right? And that's why we're putting a -2 on it, okay? Trying to think if there was another one that we could have done that too. I always make one up. Let me just put another sequence here and see what you guys think really quickly, just to make sure you know what I'm saying. Okay, so let's say it was like 1, 8, 4, 1, 2, 4. Okay, we're still multiplying by 2. This is 2 to the -3, 2 to the -2, 2 to the -1, 2 to the 0, 2 to the first, 2 squared, and 2 cubed. If I look at my first, it's right here. I'd have to back it up 1, 2, 3, 4 times. So this, if I put 2 to the n-4, it should work, okay? Because what happens for the first term? Well, when I substitute a 1 in, I get 2 to the -3, which is exactly what we want for the first term. Hopefully that helps you guys. All right. Write sigma notation. So now this one has a ... So when we write the sigma, boy, that was a terrible looking sigma. We're going to start with 1, but we're going to go all the way to infinity. We're never going to stop it. And this one's probably a little bit easier to write because the top is just counting. 1, 2, 3, 4, 5, 6. So the top is just n. And you'll notice the bottom is always 1 higher than the top. 2 is 1 higher than 1. 3 is 1 higher than 2. So if the top's n, then the bottom is n+1. Oops, not n's. I should be using i's, huh? I and i+1. Did I do that on the last one? I probably did. Let me go back and check this. I did. I had i's for my, oops, I had i's for my index, but not for my variable in the equation. So let me put i's here. Okay. It's nice to get one that's kind of simple like that after those tough ones. So far, all the formulas we've had have been explicit, which really are the best kind of formula, especially if you're a computer programmer. And the reason why they're good is if somebody says, I want the 100th term, then you just plug in 100, boom, you got the 100th term. But if you have a recursive formula, it slows down the computer, because to find the 100th term, you need the 99th, but to find the 99th, you need the 98th. And so it would have to go through all of the numbers to get to 100, okay? So it really, really slows things down. And you can, by the way, you're probably going, well, why would we ever use recursive then, right? Well, sometimes it's very hard to get an explicit formula. I remember being in college and us devoting a lot of time to coming up with the explicit formula for the Fibonacci. And then, I mean, it's so easy to see the Fibonacci if you write it recursively, okay? Like the Fibonacci, if you've never seen it, it looks like this. Basically, you add any two numbers to get to the next number. Like 1 + 1 is 2, 1 + 2 is 3, 2 + 3 is 5. So written recursively, it's easy. It's like, okay, to find any number, you take the one before it and the one before that, and you add them. It's so easy. But to get an explicit formula for this was so hard. So sometimes we just can't. And so it's easier to just write it recursively, okay? All right, so now here's a recursively defined. Now they look different in your textbook. I've never seen a textbook write it this way, where they have the a sub n + 1 here. But I'm just going to go with it because that's the book we're working out of. I don't want to weird you out when you get into like my math lab or something. I usually see a sub n in this position, and this would be an a sub n - 1. But maybe they just didn't want to use subtraction. Okay, so you'll know that you're looking at a recursive formula if it gives you a term or two, maybe more, okay? It's giving us a term. It's saying, hey guys, a sub 1 is 3. That's your clue that you're looking at something recursive. Remember, recursive, to find a term, you have to have other terms. I can't just go finding the 100th on this. Notice, for me to get the second term, I need this first term. And then for me to get the third term, I need the second term, etc. Okay? All right, so here we go. Basically, we got to find the first 5 terms. Well, the first one they gave us. So we've got to find the second, the third, the fourth. All right. So our formula is 2 times whatever plus 4, right? Basically, it's the term before. A sub n comes right before a sub n + 1. So in other words, on this one, it's going to be 2 times the one before it plus 4. So 6 + 4. The second term is 10. So on our list, we got 3, we got 10. Well, now for a sub 3, it's 2 times the one before, which was 10. So this is going to be 20 + 4. We got 24. This one's going to be 2 times the one before it plus 4. 48 + 4 equals 52. And then this one's going to be 2 times the one before it. So it's going to be 104 + 4. 108. Okay, so there's our first 5 of a recursively. Now, what stinks about this, like I said, remember on this for the first example we did, it said, and find the 20th. And it was no problem to find the 20th. Well, right now, if I said to you guys, okay, find the 20th, you would have no choice but to have to continue through finding the 6th, the 7th, the 8th, the 9th, the 10th, the 11th, just all the way until you get to 20, right? So this is why we try to get those explicit formulas, because they could just plug in 20 and you got 20. You don't even have to find any of the previous terms. All right, you guys, hopefully after seeing this video, you understand sequences, what they are versus series, and that you understand how to generate some of the formulas to give us a sequence or to give us a series, and how to use sigma notation. Thanks for joining me. Take care.